Sounds good.
So, yes, good afternoon. And it's, again, I'd like to welcome you to the Communication and Signal Processing seminar. And first, I'd start by thanking Hsieh for doing the all the work behind the scene to make it all happen. It wouldn't run without her. And I'd also like to thank our sponsors, KLA and the two research groups, NCIS and SIPML. So I'm delighted that to have our speaker today is Mahdi Soltanolkotabi. So Mahdi is, for those of you who don't know him, he's been doing a lot of exciting work on neural networks and high-dimensional statistics. And so it's, I've actually tried to have him speak earlier as well, but unfortunately we cannot have him in person, but this is the setup today. So Mahdi is an assistant professor in the Ming Hsieh Department of Electrical and Computer Engineering and Computer Science at the University of Southern California, where he holds an Andrew and Erna Vitabi Early Career Chair. Prior to joining USC, he completed his PhD in electrical engineering at Stanford in 2014. He was a postdoc in the EECS department at UC Berkeley during 2014 to 2015 academic year. He's a recipient of the Information Theory Society Best Paper Award, Packard Fellowship in Science and Engineering, a Sloan Research Fellowship, and an SF Career Award, and AFO SR Young Investigator Award, a Google Faculty Research Award. So, I mean, he's been well recognized for all the exciting work he's been doing. His research focuses on developing the mathematical foundations of modern data science with a particular focus on design and mathematical understanding of computationally efficient algorithms for optimization, machine learning, signal processing, high-dimensional statistics, computational imaging, and artificial intelligence. So Mahdi, the floor is all yours.
Great. Thanks a lot for the invitation and the introduction. I actually have enjoyed the discussions today a lot. So I'm going to be talking about learning via early stopping broadly. So this is joint work basically based on a few papers, joint work with my student Zalon, a colleague at the TU Munich, Reinhard Heckel, and another one at UC Riverside Summit, Oymak. So there are kind of two motivations behind this line of research. So the first one is really kind of understanding the learning benefits of early stopping. And so here, to motivate this, let me start with a simple experiment. And this is an experiment that a lot of you probably have seen before, which is the fact that the neural networks can overfit to corruption. So the experiment is pretty simple. You corrupt a fraction of the training labels by replacing them with another kind of random labels, but you don't corrupt the test labels. So essentially, in your training data, you take part of the training data, you corrupt a fraction of the labels. Like if it's 0, you make it an 8, and vice versa. So and then you train the network in this way, using this corrupted data. So what you observe is kind of interesting. Here I'm depicting the train accuracy. The first interesting thing is that you perfectly can always fit this data, right? So meaning that regardless of the corruption, you can still perfectly fit the training data. This might be surprising because it says that you're always achieving global optimum, right? Even more interesting here is that the test accuracy, it does decay as you corrupt more and more. So we're depicting accuracy versus label corruption. So it does kind of decay eventually, but it actually is kind of non-trivial. So that is interesting. Of course, the train accuracy with respect to the true labels, because you're fitting to the corruption, decreases, right? So all of this, I guess, is natural. So this is a well-documented experiment. It shows that the neural networks have, in principle, the capacity to fit anything, right? Because you're training it with lots and lots of parameters. And this is famously observed in this paper by Zhang et al. And including my mentor Ben Reck, my former mentor Ben Reck. So, but what is surprising here is if you add early stopping to the same experiment, and this is what we did, is that you just repeat the same experiment, but do not iterate until convergence. Actually, just stop early, pause the iterations. Then all of a sudden, something really interesting happens. So now training accuracy actually goes down. So because you stop early, you don't actually fit to the training data. But if you look at the test accuracy, it actually is consistently very high, even up to very large fractions of corruptions. More interesting, train accuracy with respect to the ground truth labels. Remember, this is something that the algorithm has never seen, right? You've just given it corrupted data, but it automatically is still consistently high. It means that the algorithm is automatically fixing the corruptions for you. So both train accuracy, both test accuracy and train accuracy with respect to the truth tables are consistently very high. And this is kind of what we wish to explain. This is kind of the motivating factor. So a second line of motivation behind this work, again, somewhat has to do with early stopping, is like learning via untrained networks. And we'll see connections with early stopping soon again. So here, the underlying premise is that, of course, modern neural networks have been extremely successful at a variety of tasks. But one catch, and I think everybody would agree about this, is that these techniques often require massive amounts of training data. And in fact, if you think about like what is the effort that goes into most data science companies these days, is really a lot of the effort goes into gathering and curating the data. And here's like a link to a nice New York Times article on this, on how much effort goes into this part alone. But of course, while this data-centric approach is great in applications such as like computer vision, NLP, and so on, where you readily have lots of training data available, maybe from resources like the internet, right? If you get to more scientific applications, gathering this kind of data might be much more difficult, right? So for example, I'm very much interested in computational imaging applications, whether it's like phase retrieval or medical imaging. In these kinds of applications, it's often not so easy to gather training data. It could either be expensive or time consuming to gather the training data, right? So that's one issue. And a second issue is that oftentimes here, you may not actually even want to solve a classification problem, like in kind of the more classical ways of doing deep learning. And so it often involves some sort of reconstruction problem. And in these problems, you're actually much more prone to overfitting. In classification, we have all sorts of cool tricks to avoid overfitting. We have data augmentation. We have all sorts of ways of, avoiding overfitting. Some of these things are really not trivial in a regression setting. So that's another reason you would want to be able to have an approach which requires less training data to avoid these kinds of overfitting. And one possible solution that is perhaps emerging is like this concept of untrained neural networks that actually don't require potentially any training data whatsoever. So just to give you an example, a famous example of this is like this behavior that you can denoise using neural networks. And so let me explain the setup. So here, I only have a single noisy image. So the only data that I have is a single noisy image. I have no other data. I don't even have the clean version of this image. So what I can do is like fit a gigantic neural network to this single noisy image. So I literally put this as my Y vector, and I just fit a gigantic neural network so that the output is equal to this, right? Via this loss. Of course, here, if I train, if I iterate this forever, because this network is large and has a huge capacity, I can perfectly fit to this noisy image, right? So that's not the surprising part. The surprising part is that if I stop these iterations somewhere in the middle and at an appropriate location, I actually get the denoised image back, right? So that is the surprising phenomenon. So in fact, basically stopping early behaves like a denoising. And in fact, here is like a different view of this, right? So basically you can see that, at the beginning, it's not doing much. In the middle, if you iterate forever, you actually get the full noisy image. If you stop somewhere in the middle, you actually get a denoised image, right? So that's kind of the paradigm. So this is one thing we would like to explain is why does this happen, basically. And this is again, this kind of experiment is quite famous from a few years ago. It's known as deep image prior. They have demonstrated that you can actually remove all sorts of interesting kinds of corruption in this way, right? You could do basically, you could do in-padding, you could do super resolution, classical denoising, you even remove some obstructions like this text in this picture, right? And so the interesting part again here is there's no training whatsoever, right? And so the common theme between these two is kind of that both they use early stopping. And so that's what we really want to focus on, right? So basically, we want to focus on these two different settings. In classification, why do you get robustness to label noise when you do early stopping? And in untrained networks, why, and more broadly, inverse problems, why do you get this denoising reconstruction effect if you use early stopping? And so these are the two things that we want to discuss. And underlying both of them is that we really have to understand the dynamics of neural network training, both train and test error, as it evolves across time. Because if you want to early stop, we not only need to understand the final point, but also the entire trajectory in some sense. And so that's going to be our focus. So let me begin with like kind of the first area, which is why does early stopping enhances like robustness, at least as far as label corruption is concerned. So again, this is the experiment where we corrupt the fraction but stop early, and all of a sudden we remove the corruption, right? So let me just explain like a little bit the underlying theoretical model here. So this is we look at a classification problem in this case. So here, the data model, you have a bunch of data points in RD, and then the output is like the class labels, right? And here we're assuming that the class labels are one hot encoded, right? Like this picture you see on the right. And so the way we're going to train our neural network is just fit a least squares loss to this one hot encoded labels, essentially, which you can think of it as just a gigantic nonlinear least squares problem. And of course, we're going to do gradient descent starting from a random initialization. Because we've used the regression loss, in order to turn it into classification, what we do is we just, at the end of training, we just, or when we want to stop the training procedure, we just pass it to a softmax and pick the maximum, right? So that's our setting, right? So this is our model and training. So we're basically just training one hidden layer neural network model to this. And to make things a little bit simpler, we are even going to fix V, and really in most of the thing we do, we just train over W. So in order to prove the results, we kind of need some assumptions on our data, but later on I will explain that these assumptions are not too critical. So we will kind of relax these a bit. So we will assume that our data are in some sense clusterable in the sense that maybe there are we already know that this is a K-class problem. We're going to assume there are in total L clusters, and each class can have multiple clusters, right, in it, right? So that's kind of our setting. So there is some sort of an assumption that the data is somehow clustered in some particular way. So this is how our kind of clean data points are generated this way. So now what to model the corruption, of course, you can take any row fraction of these basically data points and corrupt them arbitrary. So basically we corrupt S equals row times the size of the training data and corrupt them arbitrary to get our final data points, training data points. So these are our final corrupted training data points. And so again, we fit this kind of nonlinear least squares model via gradient descent. So our result, our main theory about this is that it says that, assuming two things hold. First, that the corruption level is sufficiently small, so it's a constant fraction. For example, the formal result is the constant has to be less than 1/16. And the second part is that we assume that the network is sufficiently over-parameterized in the sense that the number of parameters in the network is bigger than the number of clusters to the power 4. So that's the second assumption. Then under these assumptions, if you start the gradient descent from a random initialization and stop somewhere proportional to this, right? Proportional to the number of clusters and logarithmically in the number of corruptions, then if you stop there, the output of the gradient descent, the closest label of the output of the gradient descent is actually your ground truth labels, right? So again, we train on this corrupted data, but if you stop there, we're proving that you actually get the ground truth labels back exactly, right? So that really conforms with that kind of experiment that even up to, let's say, a constant fraction in the pictures, but up to 50% corruption in the training data, you perfectly kind of correct the corruptions, right? And so this theorem formally proves that. So that's kind of like our rigorous guarantee there. So this is more at training time. you can also prove a similar result for test time in the sense that actually, if you have data according to this model, not only do you kind of correct the corruptions in training time, right, your training data, even if you get any future test data from the same model, but it's corrupted, you also correct those, right? And so it's the same guarantee essentially holds if you have corruptions also in your test data. So this is just like universally you can fix these corruptions. So that's kind of the first result. So let me kind of before we go to like the second area, let me kind of
Mahdi,
go ahead.
A quick question on that. So when you mean that it's so you have some sample, which is your image, for example, and you trained it. I mean, it was corrupted. The labels are corrupt, and you trained it, and you got the same image again, or you got a different image from the same class. What is the result? The second result that you're saying?
So this one is like let's say basically so the first one was basically at training time, meaning that I corrupt a fraction of the training data, right? And the first result was kind of saying that so even though I corrupted some of these labels, I actually get the truth back, right? On these labels that I corrupted, right? So this is in at training time. Now I'm saying like this also applies if you actually corrupt a future test data, right? Not only the ones that you used during training, but even a new test data generated according to the same model, right? If you again arbitrarily corrupt it, right? As long as during the training time these conditions were true, then you also can fix those, right? So kind of the difference is like this result is kind of like on training error. The other one is on test error.
Can I just
thank you
for the clarification? When you say corrupt, I thought the corruption was of the labels during the training, but at test time it would be corruption of the pixel values, right?
It's still like in the labels, meaning like if your test data has corruptions in the labels, it would also fix those.
Wow, I don't understand how that could happen. It's a classifier. How can it? I mean, test data is unlabeled. I don't understand what you mean.
But basically in this model, right? Like there is a so if you in this clustering model, right? Like there still because of the proximity based on clustering, there is like a ground truth closest cluster to this, right? Which the feature will belong is kind of closest to a certain cluster center, right? And so that is what we're considering the ground truth label for that test data. And we're saying even if maliciously you actually have something else, right? So basically what we're saying is that the prediction would be this correct label, right? It's sorry, I should not have phrased it that it's corruption in the test data, meaning that any future data that I get as an input, I would also classify it correctly.
Okay, I
so this is just generalization error, not that it's corruption in the test. Yeah.
Yeah. Okay. Thank you.
Yeah. Thanks. Actually, that clarifies that. So it's just saying generalization error is 0, basically. So let me just kind of give you a rough intuition of why this is possible and why like this phenomena is beyond this very particular clustering model that we studied, right? So the rough intuition is actually somewhat simple, which is if you think about what gradient descent does in this case, so the gradient will look like if you have a neural network. The gradient in this case would be kind of the Jacobian of the neural network, which is just the rows of this Jacobian transpose is at least basically the gradient with respect to the parameters evaluated at different data points. And so that's like a Jacobian times like the residual vector, the misfit kind of between the labels and the output of the model. So that's how what gradient descent will look like here. So in this clusterable model, right, at least in this clusterable model, what you can see is that if the data is perfectly clustered, then what happens is that this Jacobian, because the data is perfectly clustered, has exactly rank L times the number of classes. So the spectrum of this Jacobian is a very low rank, right? In fact, it's exactly low rank with a certain rank. So that's idea number one in this clusterable model. Then now, if the data is not perfectly clustered, but there's some amount of the distance from the cluster centers, then what happens is that this is still approximately low rank, right? So kind of the first key idea here is that the Jacobian of these neural networks are approximately low rank, right? That's the key idea. And in fact, that's the only thing we need. We actually don't need the clusterable model to be true. We just need these Jacobians to be low rank. And you may wonder, is this true in practice, right, on real data? In fact, yes, we have done a lot of different experiments demonstrating that, for example, this is on the three-way classification using CFAR. We actually now have the entire 10 data points too. So if you use a ResNet model, if you draw the histograms of the singular values of the Jacobian, both at the beginning, at initialization, and all the way across training, you observe that there's a lot of small eigenvalues, but there's some very large ones, right? So you do kind of see at least some sort of bimodal structure in the eigenvalues. So maybe it's not exactly low rank, but there's a few that are super large. The rest are somewhat tiny. So in real data, this Jacobian structure does seem to hold. So the conclusion being that the Jacobian does have some form of low rank structure. And again, this is the entire 10 data set. Here we couldn't calculate it exactly, but we had to approximate it because it's just so costly to calculate these eigenvalues. So the second important idea that makes all of this work is that if you now look at the top eigenvectors of this Jacobian, they happen to be diffused, or they say they're not sparse, right? So they're kind of spread out, right? So that's the second key idea. And let me tell you briefly how these two ideas allow us to kind of make this work. So on the one hand, we have the Jacobian is low rank. On the other hand, we have the top eigenvectors are kind of spread out, right? So again, when we run gradient descent, you actually see kind of like a you see the effect of this Jacobian multiplying the residual, and so what we prove is something like this. So if you decompose this residual in terms of residual with respect to the true labels and then the corruption, so because we only corrupt a fraction of the training data, this corruption vector actually happens to be sparse. Okay, so that's the case in this. So now, as you run gradient descent, two things happen. Because the residual with respect to the true labels, this vector happens to be aligned with the top eigenvector, and we can formally prove this, with the top eigenvectors of the Jacobian. And therefore, because of this alignment, this part of the residual actually goes to zero very quickly because it's aligned with the top eigenvectors. It just vanishes very quickly as you keep iterating in this procedure because this is aligned with the top eigenvectors. On the other hand, this corruption, because the corruption is sparse and the top eigenvector is diffuse, this corruption is more aligned with the smaller eigenvectors, right? And so what happens is that it falls on kind of the more like the null space of this matrix, and this will also eventually go to zero, but because it's aligned with the smaller eigenvalues, it will go to zero very slowly, right? And so if you just stop the iteration somewhere in the middle, what ends up happening is you fit the ground truth labels, but you basically don't touch the corruption portion at all, right? And that's kind of the basic intuition. And in fact, you can actually generalize this in a sense that this phenomena, I don't want to get too much into the details of this, but in principle, this phenomena actually works for any nonlinear structure, including a deep neural network, right? At least like this underlying phenomena, as long as you have some more technical conditions, but essentially as long as you have this behavior that the Jacobian is low rank and the top eigenvectors of the Jacobian of the network is diffused, then you can essentially prove in some ways that the output of the network when you stop early is in some sense close to your ground truth labels, right? Again, this is a little bit more technical, so I'm not going through the assumptions very carefully, but my point is that essentially these low rankness plus diffuseness of the top eigenvectors are really the key assumptions, not that the data is kind of like clusterable or anything. Okay, so that's kind of like the finishes kind of the first portion of the talk, which is how early stopping allows you to remove corruptions in your training data. and also get perfect generalization error. So now I'm going to switch to kind of the second problem, which is how does early stopping allow you to kind of do image reconstruction and denoising? So again, this is the experiment where you have a noisy image, and if you stop early, the iterations early, you actually get the denoised image back. And here's a different picture just to get some intuition again why this works. Is roughly because, intuitively at least, it's because again, if you have like a noisy image, you can decompose it into the signal part and the noise part. What happens is that when you use a neural network, you actually end up fitting the image much faster, similar to the phenomena we were seeing in the robustness case. You end up fitting the image portion of the data much faster than a noisy portion. And so if you stop early, because you see a superposition of these two curves, if you stop early, then you actually get the denoised image back, right? So underlying somewhat is similar, except that here you don't have any training data, unlike the previous case. In fact, this is kind of the interesting part is that using this approach, again, the denoising, of course, is a well-studied problem, and there's a lot of good solutions for it. But using this kind of simple approach, one may even think a somewhat naive approach, you actually do match the performance of some of the best denoisers out there. Like, for example, here in the paper, we have comparisons with BM3D, right? So that's the interesting part. Of course, our main interest is not denoising, because denoising is a well-studied subject. It's kind of saturated in some sense. But of course that you can also use it in image reconstruction task, as I will explain soon. And as I mentioned before, this also works for other kinds of corruptions as well. Okay, so now we want to explain this phenomenon more theoretically. So we need to here understand two things, right? Which is like, which kind of architectures enable this phenomenon, right? Clearly there is no magic, right? Like this is, you cannot just denoise any data this way. So somehow there should be some properties of the architecture, which is kind of like captures some good information about the images, right? So that's what the number one thing to think about if we want to talk about theory. And the second aspect is, really again understanding what is exactly the role of early stopping here. So let me explain the kind of network that we use. So this is actually kind of a modification of this deep decoder, which itself is a modification of deep image prior. So the structure is that you kind of have your input in form of multiple channels. So imagine basically these are RGB colors. So each channel in your input is one of the RGB colors. So each column in the input is basically a vectorized version of the image in one of the RGB channels. So then you pass it through a convolutional layer and a ReLU nonlinearity and some form of normalization. So from one layer to the next, this is what it looks like. So UI is a kind of a circulant matrix or a subcirculant matrix modeling the convolution. So BI is like the output of the previous layer, and CI is kind of the coefficients with which you combine it. In the final layer, we don't have any ReLU nonlinearity, so you get the output. And so I couldn't resist putting a picture of Malibu here, right, for advertisement. But in this kind of approach that we're using, we don't even train for the convolutional layers. We even use fixed convolutions, and this is actually what is different from the deep decoder. We don't even train over that, we just have a fixed interpolation kernel. What we do train for is like these, how you combine these. So we train for the CIs essentially, or I shouldn't call it training. We just optimize over the CIs, because again, there's no training data. I do want to point out that the difference of this kind of network compared with the original deep image prior is that in the deep image prior, you not only have this decoder portion, you also have an encoder portion. And one of the main insights of this deep decoder paper that I've mentioned in the title is that they realize that actually the second part is completely unnecessary. And you can get as good of a performance if you just remove the entire second part of the network. This is obviously great because you have to optimize over fewer parameters. So to analyze this theoretically, we actually just look at a one hidden layer model, right? So in this case, kind of the network will look something like this, right? So in principle, you have to train over both C1 and C2. U, again, remember, is like a circulant matrix or a subcirculant matrix modeling convolution. B is the input, for example, RBG channels made into a form of a column. And so for simplicity, we'll do one further simplification, which is we also assume the last layer is fixed. In practice, this also doesn't seem to matter much. So we only really, for the theory portion, we only really train over these C1s, the input, these sets of coefficients, right? But even though we don't optimize over the kind of the convolutions, obviously we expect like the form of this convolution is also clearly very critical. So what happens is, but what we observe and our theory kind of predicts is critical is that kind of like is not how the convolutional the convolution kernel is in this domain, but in kind of like a nonlinear Fourier domain, right? So essentially, given a convolutional kernel, we form like a dual kernel, which you can essentially think about it as like applying essentially some sort of Fourier transform combined with some sort of nonlinearity. The details of that is not important, but what is important for our theory is that this dual kernel, which is kind of like a transformation applied to the normal kernel space, in this dual kernel space, the kernel should decay very quickly. That is the critical aspect, right? So the kernels that are good is for this kind of application scenario, at least for our theory, is that these kernels should decay quickly in this dual space, if you will. So we've kind of now talked about the architecture, including the convolutional kernel that would work here. The second important ingredient is that what signals would work in this case, right? Corresponding to these kernels, convolutional kernels, what signals can you denoise or reconstruct and so on, right? And so it happens that for this kind of kernels, right, the ones that have like this, the sharp drop in the dual space, essentially the signals that are used are essentially low pass signals. It's not exactly low pass in a Fourier domain, but in a related trigonometric basis, but they look very much similar to Fourier domain, right, as you can see. But they're slightly different essentially. So now, now that we have all of the ingredients, I can finally tell you what our main conclusion is. So our result for denoising is that if you have a signal which is supported kind of on the top P trigonometric functions in that space that we just discussed, and then you add Gaussian noise to it. Now, if you fit a generator, a convolutional generator like we discussed, where the width of the network is sufficiently large, right, in terms of the number of channels, if this is sufficiently large compared to the output dimension, then with high probability, if you stop somewhere early, which we kind of characterize, right, then what you get is actually you get the kind of the min-max denoising rate essentially, right? Basically, if you think about the signal having p degrees of freedom, you kind of get square root p over n, right? So this is kind of the rate you would expect for this kind of simple denoising, right? So if you stop early, you actually get the ideal denoising rate, if you will. So this in some sense says that if you think about it, for one hidden layer neural networks, what we're kind of claiming is that fitting this convolutional generator combined with early stopping essentially operates in a similar fashion to Fourier thresholding, right? This is just for one hidden layers. We don't, to be honest, we don't completely understand what happens for a deep neural network. So this is something we are still trying to figure out, right? But it does seem like even, even these trigonometric basis approximations, they're somewhat okay. Obviously, like a deep neural network is much more nuanced, right? But if you look at the eigenvectors, right, instead of the eigenvectors of the Jacobian, then you don't exactly get the Fourier basis, but you do get related phenomena somehow, right? So you of course get much more elaborate basis functions, which we don't know exactly what they are, but they seem to be somewhat related to these Fourier-like features, right? But they're obviously, as you can see, they're much more nuanced. But the point is that in general, for a more general nonlinearity beyond one hidden layer networks, what like the corresponding features should be is actually again based on these eigenstructure of this Jacobian matrix of the neural network, and that's what we're trying to depict here. So let me also try to quickly demystify this. It's actually somewhat related to what we just discussed. So here in the previous example, so here in order to demystify this, so this actually starts with a linear problem, right? So for a moment, let's actually forget about this kind of nonlinear denoising. Let's just imagine we just had a linear problem where you're just trying to fit you have a noisy signal, right? You're trying to fit using the dictionary J, and you're just fitting C, right? And then you stop somewhere, and your estimate is going to be this dictionary times your coefficients, right? And obviously, you do this via gradient descent. If you think about, this is a linear problem, so we understand everything about the dynamics. In particular, as we expect, the dynamics are controlled completely by this dictionary matrix, right? By the eigenvalues and eigenvectors of this dictionary matrix, right? And in fact, it's very easy to kind of prove a simple result like this, which is like the difference between the output of the model after a certain number of iterations minus the ground truth signal, right? Is kind of it can be decomposed to two terms. One term you can think of it as the error in fitting the signals. The other term you can think of it as the error in fitting the noise, right? And you can derive these formulas precisely. So now if you stare at this linear equation, right now it might not be clear why this decomposition is interesting at all, but now let's pretend that the signal is actually correlated with the top p eigen vectors of this J, which is also low rank. Then two things will happen. Because of this correlation and the fact that this is low rank, most of the signal is fitted very quickly, because this quantity that we see here is actually much, much smaller than 1, right? So this is actually very close to 0. Whereas because this J is low rank, the smaller eigenvalues are extremely small, right? So this is practically 0. So this entire thing is actually practically 1, right? Which means that the whole thing is actually 0. So it means that again, you don't fit the noise at all, right? At least in the early iterations, because again, it's the same phenomenon. The signal is aligned kind of with the top eigenvectors of the Jacobian. And so you first fit those directions, right? And then it's only later that this term, which is the term that corresponds to fitting the noise, it actually picks up energy, right? And again, the two key things is because the signal is structured and aligned with the top eigenvectors, and the Jacobian is low rank and it has this sharp drop, right? So what happens in the nonlinear case is essentially, at least for this one hidden layer networks, so it's a similar phenomena. Instead of the eigenvectors of this Jacobian of the linear case, what we end up having is actually like essentially these trigonometric bases that I explained. And instead of these singular values of this J matrix, you have the entries of the dual kernel, right? And this is why I said that this is important for this dual kernel to die out very quickly, because this implies that again, you have this low rank behavior essentially, because if these drop down very quickly, most of them are 0 except the top ones. And so the error in fitting the signals, similar to the linear case, goes down very quickly. So you fit the signal very quickly. You do not fit the noise that quickly. So you do pick up a little bit of noise, but not too much. So if you look at the aggregate error with respect to the ground truth, you actually do a relatively good job at denoising overall because of this phenomena. And again, here, these W's are this trigonometric basis that I discussed, and the sigmas in the nonlinear case are entries of this dual kernel that we defined earlier. So this is just another kind of depiction of the same phenomena. So we are actually looking at the coefficients in this trigonometric basis. So this is the overall error. So you can see the error, the portion that corresponds to the signal, it dies down very quickly. So if I stop it here, you pick up some, you basically the signal portion, the error with respect to the signal, the error in fitting the signal is actually practically 0. you pick up some noise in these coefficients, right? But not too much, especially in these other directions, you don't pick up any noise. And this is why if you stop here, you do somewhat a relatively good job at denoising. But if you let these iterations continue, then you pick up a lot of noise that maybe you didn't want to pick up, right? This is why you should not iterate forever. So you should kind of stop when you essentially have managed to fit the signal. So somewhere around here. So then you get somewhat a sensible kind of denoising performance somewhere around in the middle. So that's kind of the main intuition in this nonlinear case. So the interesting part is that all of this works also not just for denoising, but if you plug it into a compressive sensing setup, right? So in a compressive sensing setup, what we have instead of a noisy image, right? What we would get is a kind of undersampled measurement of the ground truth, right? Here X. So now instead of like using a regularizer as we would do typically in this area, especially like since compressive sensing, instead we just we put a neural network instead of like the modeling of the image, right? So and then we run gradient descent on this, right? So this time is kind of interesting that you don't even need to even do early stopping in this case. This is because of the measurement model essentially. So and this one is a little bit more technical, but roughly speaking, what we show is that if you again have a sufficiently over-parameterized two-layer convolutional generator, if you run gradient descent even up to convergence, you recover basically a signal like you can recover a p-smooth signal, right, from order p kind of random measurements, right? So p-smooth is again meaning that a signal which is smooth in this trigonometric basis expansion that we discussed. So that's roughly the result. And we did kind of like at the time we were kind of working against a deadline. So we started by doing more vegetable MRI kind of things because just the data set was a little bit smaller and more manageable for us to handle. And so you can see on this vegetable MRI data set, the data you can actually do get if you, I think this is a factor, this one is actually legitimately factor 8 acceleration, right? So you have the factor 8 undersampling, if I'm not mistaken. And then so these are kind of the results you get. This is the loss. This is the loss with respect to the ground truth image, and you can see that you do a perfectly good job of, a reasonable job of reconstructing. So since then, both us and actually my colleague at TU Munich, so this is actually based on his work, this part. They've done more extensive experiments of using this on basically more realistic MRI data. And so what they've observed is that this is the factor 4 acceleration. What they've observed is that using this approach, which in this context they call the COM decoder, they do more or less match the performance of TV regularization techniques. In fact, they exceeded, and also they match the performance of simple trained neural networks. So these are not exactly state-of-the-art neural networks, but these are units, but which work reasonably well, but they're not state-of-the-art. So it's not that we can still match fully trained approaches right now, but at least we can do as well as some of them, including like these unit structures. Again, this is work by my colleague at TU Munich, and so they actually also do a good job of looking at a bunch of different metrics, not SSIM as is just common. They look at VIF, which sometimes it seems to be a better metric. They also look at PSNR and all sorts of other metrics. So this is their result. So it kind of shows some promise even when you go fully untrained, even compared with trained deep learning approaches. This is also an independent study along similar lines by Mickey Lustig's group at UC Berkeley. They've also made similar observations that it does seem to be these untrained structures that at least seems to become competitive to more classical kind of compressed sensing techniques which are based on TV regularization, and of course also similarly don't require any training data because they use more prior assumptions on basically the model. So let me, I think I'm essentially out of time. So let me actually wrap up here. So kind of what I discussed is kind of like the utility of early stopping, broadly speaking, in two different contexts. One was that sometimes if you use early stopping combined with over-parameterization, it has this intriguing property that you can remove label corruption from your training data and achieve perfect generalization error on your test data, even though you had corruptions in your trained data. So, and the second one is that, it also helps you do the early stopping in the context of untrained neural networks, allows you to do a variety of image reconstruction and restoration tasks. And the main intuition there was that these convolutional generators, that is the end message out of this, is like they kind of behave in some sense similar to nonlinear PCA. They basically learn different modes in your signal or data at different speeds. And so if you stop early, you could, if the modes are aligned with your signal, you end up learning the signal portion and not fitting the noise or the noise caused by undersampling, right? And finally, that untrained networks, if you use them in a compressed sensing framework now, even without early stopping, they also lead to this intriguing kind of regularization effects. And so that's kind of the third conclusion. And so here are kind of the link to the papers we've written on this subject. And then let me stop here. Thank you.
Thanks, Mahdi. So I think we have two discussions. One is Guanha.
Yeah, Guanha.
Why don't you start, and then I'm the second one. I will proceed after that. Right? Yeah. And then we can have questions after that. Right? So yeah, go ahead.
Okay. Thanks for the exciting presentation. And can you see my screen?
Yes.
Yes.
Okay, yeah. It's very exciting to see the combination of the untrained neural network and the compressed sensing application. So overall, this work demonstrates that the deep decoder can solve the compressed sensing or image impending problem by simply gradient descent, and not like the natural image denoising problem, where we should do early stopping to prevent the overfit on some noise. In compressed sensing implementation, we could do as many iterations as we can, because more iterations will lead to better results. That is very important in real setting, because it's not easy to know when to do the early stopping. And more importantly, this work provides a theoretical upper bound of the error between your estimation and the real signal. And there is a two hypothesis assumption behind this upper bound. One is that your signal or your image should lie in the span of the major of the low or the low frequency single vector of the upsampling layers, which is the case in the deep decoder. And the second assumption is that the singular value of the sigma of the upsampling layers should decay, of the Jacobian should decay pretty fast, like geometrically, and that's usually the case. And beyond this, we have some questions. One is in the paper, in the theoretical derivation, the step size should be less than the reciprocal of the square of the spectral norm of the Jacobian. But in the real setting, do you have some insight of how can we determine the step size should be?
So yeah, that's a good question. Unfortunately, it's not. There is no like. I don't think we actually tried exactly 1/sigma 1. Although this one I think should work reasonably well. But like everything else in machine learning, in practice you actually just tune this, right? So
yeah.
So unfortunately, the theory may not be very predictive of like picking the right step size. I do think that for this particular thing, probably this step size is not completely off, but I still think you will gain a lot by kind of adjusting it as you iterate and so on. So some tuning will definitely help though. So we don't really have a good answer how to pick the step size well. So this is just a rough upper bound.
Yeah, thank you. Another thing is that in this paper, the network structure is more like a deep decoder, where the kernel size is like 1 by 1. So do you think if we change the kernel size to like 2 by 2 or 3 by 3, will this improve the reconstruction quality? I saw in your results there is a convolutional decoder for the MRI experiment.
Right. So, yeah, actually, I think if I'm not mistaken, Drawinghard has done some experiments where you do see some improvement if you use higher order, right? Like instead of 1, as you say, 2. But so from what he explains, my understanding is that somehow like training becomes a little bit, or the fitting problem becomes a little bit more complicated if you do that. So computationally, you kind of lose a little bit, right? So his conclusion has been that probably 1 is like a sweet spot, which like you don't pay a lot in terms of computation and it works reasonably well. But you do get some improvements if you use higher orders here.
Yeah.
So this has been his observation.
Yeah. So last question is that for now in the theoretical derivation, the measurement matrix is restricted to some Gaussian random matrix. Do you think that still the theory still holds true for other kinds of sensing matrix?
Yeah, that is a very good question. I think underlying this theory is really, it is not heavily reliant on Gaussianity. So basically, essentially any kind of sketching matrix that preserves low subspaces, right?
Yeah.
So basically all you need is that, so you need the following property, that on a p-dimensional subspace, which is not aligned with your A, you basically preserve vectors on a p-dimensional subspace, right? So that's what you need. So certainly this is true about Gaussian matrices with order p measurements, right? But this property is also true if you have like Fourier random sign matrices, for example. So basically, although we have not worked it out precisely, basically what I'm trying to say is that as long as your matrix has some sort of JL property, right? Like any kind of matrix that you can plug in a Johnston-Lindenstrauss lemma, right? You should be able to also plug in eventually in this result.
Yeah.
So randomized Fourier, meaning like you randomly sample the rows, you multiply it by diagonal sign matrix, IID sub-Gaussian, sub-Gaussian rows. Those kinds of vectors should in principle work, but you would probably incur some log factors, extra log factors, which we don't have in this result.
Yeah. So in the application side, we are very impressed with reconstruction quality under a very high acceleration ratio. We would like to suggesting that comparison with some traditional compressive reconstruction, but in your slides, you compare that with a total variation regularizer and have improved results. That's very impressive. So we are suggesting that, we are not using any historical information for our neural network training, so we can regard it as some kind of blend learning method. So maybe compare these methods with other kinds of blend learning method. For example, we learn dictionary as a sparsity regularizer could be another interesting comparison.
Yeah, that's actually a very good point. I think that would definitely be an interesting comparison. So it's actually very good that you're mentioning this because we are, as I was mentioning to you and Jeff, that we are kind of looking further, and so we were also actually kind of wondering what other baselines is there that we should be comparing to. So this is actually very useful. Yeah, thanks for the suggestion.
Yeah, thank you.
Let me do a screen grab of this. Thank you.
Yeah.
So the video will be up on, there will be a video on YouTube, so you can also look at it when that's
Okay,
up.
perfect. Thank you.
Does not, yeah.
Yeah. And though we can run as many iterations as we can for the compressive sensing application, but there are still questions for the real clinical setting because we can not afford such a long reconstruction time. So do you have some idea of if when the image quality is good enough so we can stop the iterations?
Right. Again, this is an issue that, we don't have a really good answer. I should also clarify one thing, that even in a compressed sensing scenario, even though we proved that even if you iterate forever, you still get a good result. Yeah. In practice, you do observe some mild improvement if you stop early, right? Basically, you know, like the curve does at some point go up eventually, but it only goes up very slightly. So that kind of, it doesn't matter. And yes, you can also see that here, the curve does creep up a little bit toward the end. And so even in a compressed sensing scenario, we do think that it might be good to stop somewhere. It's a little bit better to stop early. Yeah. We just had, you know, we haven't, both theoretically, for this one, both theoretically and practically, we haven't figured out a good answer to this. One thing that actually Reinhard did recently, right, in this context, my co-author did, is that basically he kind of tried tuning that on the training data, right? Meaning like he took a very few training data and tried to calibrate when to stop based on so some part of the training data, for example, in fast MRI, right? And so this approach kind of reasonably worked well. So at least to decide when to stop, but it's still, again, from what I understand, it's still not as good as you know, like a completely trained network, right? But this approach did help a little bit, right? So use part of a training data essentially to decide when to stop, right? So in some sense, you know, train at least one parameter, which is when to stop.
Yeah, that should be a very good and practical solution.
Yeah, but I do feel like this is, you know, this is a really important question that you're touching upon, because to me, that's it would be very nice if we had like the early stopping step based on the theory would actually guide us a little bit better, but unfortunately, it's not the case right now.
Yeah. And our last idea is that maybe we can combine the iterative reconstruction and the proposed untrained network as some kind of structural prayers. It will be very interesting.
So you mean like in an iterative sense, you kind of pass it through a network as you're iterating?
Yeah, I mean, in some iterative steps, we could plug in the untrained network as some kind of prior or regularizer.
I see. Right, that's kind of like you denoise as you iterate. Like it's kind of like almost like a Istel-like algorithm, right? Or Fistel-like algorithm. Yeah, that's very interesting, actually.
Yeah,
I agree.
Thanks for your talking.
Yeah. Thanks, Glenn. So if you can stop sharing, I'm going to share next, right?
Yeah. There's some problem with my Zoom. Maybe you can directly start sharing. Can you?
Okay, I'll share it. Yeah, no problem. Microsoft SharePoint. I don't know which one. Oops, no, sorry, it's not that. I'll just share screen. Okay. All right, Mahdi, thanks a lot for a very interesting talk. So I'm just going to try to be a little bit more high level. I don't know if you can see my slide or not. Hello?
Hi, yeah, we can see your slide. Thank you.
All right, great, yeah. Okay, so I was just going to give a sort of high level overview of the theory results. So in some sense, one of the main messages is that the architecture of neural networks is sort of a low dimensional structure. And when I call it excited or initialized by isotropic weights. Also full rank in some sense, all the entries are non-zero. So Jacobian is in that sense universally sort of a low rank subspace, low dimensional manifold, a sparse basis expansion in all the theories. And the top eigenvectors are sort of diffuse. That's one of the things that messages that comes out of this work. So then where the rest of it is sort of saying if the sample or the signal that you have is structured as in it's some structured signal plus isotropic noise in the labels, then the signal structure is very close to the neural network structure, and then basically the output of the initialized neural network will be closed itself, and a few steps of gradient descent will help latch on to the correct signal structure. And if you train any further, you start fitting to the noise, and so you should stop early. I mean, this is sort of a very intuitive summary of the results. So based on this, I had a few questions, and these are again very high-level questions, not as detailed as the other ones. So one was more in terms of the sort of SNR type thing. So your results had an SNR property, which is saying only so many, this fraction was corrupted. I can interpret that as an SNR. So it's something like the corruption is at most such in the samples in the neural network to work well. But so plots don't seem to have that. I mean, you are even going up to 70, 80% level of corruption. Is this a disconnect between the theory and practice, or something else, something to do with the data itself that you were running, showing the plots on, or different data sets will give you different performance?
Right. Yeah, that's a very good question. So again, like the theory is obviously not perfect because especially the theorems that I discussed is under a clusterable assumption, right? In some sense, it's assuming that the features are sufficiently clusterable. And in that case, you know, this assumption is kind of okay for something like MNIST. You can actually, it's probably an okay assumption to model MNIST as a clustering scenario where each class could have multiple clusters. It's not so great maybe on CFAR, but what we do observe in practice is essentially that you know, the fact that how large can you go, like 80% versus 50%, it does again depend on how aligned this signal structure is with the top eigenvectors. And so for something like MNIST, it's actually surprising how far you can go. Like we were actually surprised that you could go all the way to even 80%. So on something like CFAR is a little bit more moderate. Like I think we did experiments on CFAR 10 and then fractions of CFAR 100. And there we could, it's not all the way to 80%, but we could go all the way to 30%. So yeah, the signal to noise ratio, how much fraction you have does depend in some sense to the basically the structure in the data. What happens is the reason you don't see this very clearly in the theory is that because in the theory for the clusterable model, right, like the clustering assumption kind of you wouldn't see that. In a more general theory, it would show up in kind of like how low ranked this matrix is and what is the eigengap, right? So if like you have more eigengap, then you kind of can push this constant fraction a little bit further versus when you don't have this eigengap essentially, or it's smaller.
Oh, thank you. So I'll go to the next one. This is more in terms of looking at the main result and sort of thinking more about what would be adversarial noise, because your noise is basically in some sense like isotropic noise, maybe some variations of that. So the results seem to indicate that an adversarial noise of the same structure as a neural network subject to some SNR type conditions will cause the untrained network to fit noise more. So in that case, is it better to actually train fully, not use the untrained one, but actually train much further out? Or how would you sort of combat adversarial noise if you have anything of that kind?
Right. So I think that's again a very good question, because so if you actually add adversarial noise in the sense that the noise is aligned with the top eigenvectors of the Jacobian, actually the early stopping wouldn't work too well, right? Because as you were seeing, you would fit the error in the signal in that subspace or in those directions well, right? So it means that you would actually fit to the corruption, right? So early stopping would be still a little bit better because you would not fit to the other kinds of corruptions that you may have. But definitely, if an adversary manipulates your noise, right, then this wouldn't work unless if your kind of like noise, even if it's adversarial, has additional structure. Like for example, this is what we saw in the first part of the talk. If your noise is adversarial but is sparse, right? So then if the eigenvectors are diffuse, then you're again okay. But a completely powerful adversary which could corrupt any direction, yeah, that would not work in this case. Early stopping cannot help you basically.
Because in this adversarial context, you could assume that the adversary knows your the neural network structure, right? I mean, that's usually the context, in which case then you can find out what is the eigenstructure and everything in some loose way.
Exactly. So I would say if you actually go in the direction So actually, we believe that one kind of interesting way to construct these adversarial examples is like, if you pick the direction which corresponds to the maximum eigenvalue of the Jacobian, that would probably be very bad here. So that kind of malicious adversary can really screw up this untrained network.
All right, thank you. And then the next sort of question was more about generalization. I think you mentioned it roughly at the end, but there's been a lot of work on either taking the mean field limit and analyzing the SD, or taking an optimization viewpoint and studying the where the global optimum, and then use that to comment on generalization. So how are the generalization results determined in this untrained setting? What is the contrast and what?
Right. So there are kind of results in this untrained network kind of fit into a different category of generalization results, which is kind of like based on what is known as like a neural tangent kernel regime. This is a regime where the network is sufficiently wide so that kind of the Jacobian at initialization is kind of predictive of the final performance of the training, right? Which means basically what it means is that the performance that you get out of the neural network is comparable to a kernel obtained by essentially using a linear structure where you use the Jacobian at the random initialization. So it's essentially like comparable to a random feature model, essentially speaking. What happens in practice is that if you initialize much smaller than like our theorems and results require, right? In this other regime, which is sometimes referred to as the mean field regime, then you might be able to even improve on this kernel regime with neural networks. And so there's a lot of interesting observations that actually in this other regime where you initialize smaller than you would need to, or with lower width than you would need to, as what predicted by our kind of theory, which is like the NTK kind of theory, then you could even learn more interesting phenomena, right? Meaning like your generalization performance could be even better than what one can prove in this NTK regime. And there is really a kind of one of the most pressing mysteries, in my opinion, on the generalization of neural network these days is actually resolving that challenge, which is like, can we actually show why neural networks work even better than this NTK regime of analysis suggests, right? Yeah. In the context of untrained networks, it could be that instead of like this Fourier thresholding that our theory concludes, they could be actually, even for one hidden layer networks, this kind of thresholding could be in a different sense. For example, this thresholding, if you think about it, Fourier thresholding that we discussed is kind of in L2 Euclidean sense. Maybe if you kind of have shallow neural networks with lower width, maybe you get actually a more sophisticated phenomena out of neural networks. But this is not something that unfortunately our theory can cover. But it's a very interesting direction.
Yeah, so I had two other questions which are sort of, I think, going that direction. What happens if you, instead of using stochastic gradient descent, you use something like stochastic mirror descent? So you change the training algorithm itself. And the second one is maybe tying to what you were saying. So some of the initialization, as I said, it seems like it's a full, the weights are chosen Gaussian, IID Gaussian. What if I did not use the isotropic? I mean, there was some sparseness that I basically few of them were zero, or I did not use Gaussian, I used some heavy tail distributions. How would that change the structure of the neural network? Or would those things not be, it's not robust to many of these, those assumptions or not? It's sort of a question that I have, more speculative.
So with respect to the first one, I honestly don't have a good intuition what happens if you use like a different geometry, but I think it's a very interesting question. So the second one I can kind of give you, the second one I'm a little bit more optimistic in the sense that I think I might know the answer to it, which is at least if you look at like the random feature models that they were developed at the tail end of the kernel learning approaches, including like this random kitchen sink and so on, people have actually more recently observed that if you, instead of these random Gaussian matrices, weights, you use, which does correspond essentially to a randomly initialized neural network, these random kitchen sink models. If you, instead of the Gaussian thing, you replace it with basically Fourier multiplied by random sign or convolution, the random convolutional structures, it does seem to work as well as the random feature model. So this is kind of, you know, in this area, they've stayed with the food analogy. I believe they call it fast food, right? So, there are these random feature models, which are kind of the fast food version of random kitchen sinks. And so based on that, I would say that probably this kind of structural behavior does carry over to those kinds of initializations too. But this is not something that we have tried. It would definitely be interesting to try.
So those are all my questions. So I'm going to stop sharing. Stop sharing. And any other questions anyone has, please feel free to ask them.
This is Jeff. I'd love to jump in with one here. So thinking about the first, but fascinating presentation, by the way, really great. So the first part, we've got training data that's corrupted with wrong labels, yet we're using a loss function to train that's not robust to outliers or errors, right? And then we're saved miraculously by the fact that gradient descent converges slowly on the components where the errors are. But of course, you know, we might hope in the future someone will invent a, you know, quantum computer that can solve these optimization problems really quickly, right? And so this is kind of philosophical question coming from somebody who sees ML as meaning maximum likelihood, not machine learning. When I see the abbreviation still, right? I'm old school signal processing. Wouldn't we, is this the future of relying on these properties of gradient descent, or can we set up loss functions that are robust to the errors in the first place and maybe get even better performance?
Right. And so I would agree with you that, you know, like this, you know, it's a little bit, you know, unstable to use results based on when to stop and stuff like that. So the hope is that you can kind of decode the appropriate regularizer out of this, right? For example, you know, one could even think like early stopping might be equivalent to minimizing some sort of distance from initialization in an L2 norm. So actually people have tried this in this context. That would not work as well as doing early stopping. My personal belief is that if you add a weighted regularization on the parameters, meaning that you have like theta minus theta 0, right? You minimize the distance from initialization, but instead of a 2 norm, if you use a weighted norm, something like that should work as well. But you know, I have not been able to figure out the mapping between the two, right? So essentially, I believe there is a regularizer that corresponds to this phenomena, but I don't know exactly what the coefficients of that regularizer should be. Okay. And I should say there's actually even, you know, there's some follow-up work, and I think even Carlos might be talking about some of this. He has a different regularizer in the first context that actually does improve things. Like I think in the workshop that you were mentioning, he might be talking about it. So there's some interesting work there too.
And then one last really quick sort of implementation level thing. You have a sigmoid, I believe, at the end of the neural network architecture you showed, and I'm curious how you do that in MRI, where we don't necessarily really know the range of values, right? So, because the scans can have vary greatly in their intensity, so setting the upper and lower limits and the sigmoid is not so obvious to me.
Oh, so I think in the last layer we don't have anything, so we just have values in the middle.
Oh, okay, I see. That was a different part. Okay, great. Thank you very much. This is really interesting.
Thank you.
So Mahdi, thanks a lot for a fascinating seminar. So I'm going to clap. So anyone clap or not? And I think people.
I really actually enjoyed all of those questions. This was great. Thank you.
All right. Thanks a lot. All right. See you soon.
Bye.
Bye.